Hello everyone, welcome to Gatewala. My name is Venkat Rao. So, having 15 years of experience teaching GATE students, especially I am teaching theory of computation and compiler design subject. In this series, we are discussing about compiler design subject. Yesterday, we have completed one of the session on lexical analysis. So, as in yesterday's class, lexical analysis of compiler, how a lexical analyzer program of a compiler is going to work and how the outputs produced by the lexical analyzer. What is the role of the lexical analysis in compiler? All these things we have discussed. Thank you, Ramrup. Thank you. Someone saying happy Teachers Day. Welcome, welcome. Good evening, everyone. Welcome. Thank you. If any teachers are there, maybe some teachers may listen there for learning of the subject. For them, I wish them happy Teachers Day. Right. Okay, students. So let us continue our discussion on compiler design. So I welcome all of you to compiler design subject. In yesterday's session, we have completed one of the topic of compiler. So before going to start the actual topic, let us see what we have discussed in the previous class. See, these are the topics I think we have seen in the last class. These are the topics which are there in compiler. First one is a lexical analysis. This course compiler design is for GATE point of view. So I am discussing compiler design here because compiler design will be discussed in practical orientation like writing programs using some tools. But for GATE point of view, writing programs using tools, all these are not required. We have to study theoretical point of view. So what are the theoretical concepts that are used in compiler? So we are discussing theoretical topics of compiler which are used in every phase of the compiler. Okay, so these are the topics. These topics directly I have taken from the GATE brochure. These topics are as per the GATE syllabus. So what are the topics here? Lexical analysis, that is what we have completed in yesterday's class. Next one is parsing. I told you in the last class 50% weightage will be there. 50% weightage will be there for this topic parsing. Parsing is one of the very important concepts in compilers. So majority of the question, almost 50% of the questions, assume 6 marks are given, 3 marks will get from the parsing itself, sometimes more also. So this is the weightage of parsing. In today's class, we are discussing on parsing. Okay. So before going to start parsing, let us see the actual diagram. So in yesterday's class, I told you compiler is a very big program. So the task of the compiler subdivided into multiple subprograms. The task of compiler carried out by so many different programs. There are mainly 6 programs here in compiler. So compiler design means designing of each of this program individually. We have to design each of this program individually and attaching them, then we'll get the compiler design. That is what actually compiler design is. Right. So in this, the last class we have seen what is the task of the lexical analyzer. Lexical analyzer taking high level language as input, and what is the output of the lexical analyzer? We have seen in the last class about lexical analyzer clearly. Output of the lexical analyzer is called as tokens. And only some of the errors of compiler is doing two things. One is a translation, high level to low level. One more is error detection. So error detection, if you say the lexical analyzer part will detect only some part of errors called as lexical errors. Lexical analysis has the capability to identify only lexical errors. And lexical analysis don't have the capability to detect syntax and semantic errors. That's why tokens are sent to the parser or syntax analyzer. Now syntax analyzer is taking these tokens and performing parsing or syntax analysis. This is also called as parser. There are two names for this syntax analyzer. We can say syntax analyzer or parser. The input to this tokens, output is nothing but parsed. So if any errors present in this, the type of errors detected by, if any errors present in the program, this phase will identify the errors detected by syntax analysis or syntax analyzer or parser known as syntax errors. So in today's class, our discussion will be on this. Not only in today's session, in the coming 3 to 4 sessions, our discussion will be on this, because syntax analyzer is the most important part of the compiler. Majority of the concepts, majority of the questions in the gate will get from this. So let us discuss about syntax analyzer, how syntax analyzer will be working here. See, this is the role of the lexical analyzer. Yesterday we have seen it is producing tokens. Now these tokens are given to syntax analyzer or parser or syntax analyzer. What the parser will do? Parser produces parse tree. It takes tokens and produces parse tree. And not only this, parser will, to design this parser or syntax analyzer, we have to take context-free grammars as input. Context-free grammars as input. So let us see what is the exact meaning of parsing and everything. So we have a concept called as parsing here. Parsing. So what exactly parsing is? There are so many concepts involved in this. Let us see all these concepts one by one. Syntax. First, what is syntax? So the name of this phase is also called as syntax analysis. Syntax analysis or parser or parsing. So these names include having some terminologies. So first, to design this phase, we should understand what is the meaning of some of the terminologies. First of all, what is syntax? Syntax is nothing but structure of the source program is called as syntax. Structure of the programming statements. So we'll say, while learning programming language, you say this is the syntax of for loop. This is the syntax of if-else statement. These are the syntax of conditional statements. Syntax means structure of their statements. Every statement of a language having particular structure. That structure is called as syntax. That structure is properly there or not there, verification is going to done here. So that's why this phase is called as syntax analysis phase. We are analyzing the syntax, whether it is properly there or not. Right. Now we have a terminology called as parsing. What is parsing? Parsing is one of the concepts from grammars. So what is parsing here? Checking given string is member of given grammar or not, known as parsing. Checking a string is member of the grammar or not, that is called as parsing. So if I give one context free grammar or any grammar and a string w, this string is belongs to this grammar or not, is w belongs to this, whether the given string is generated from given grammar or not. This is called as parsing. Why this parsing name is given to syntax analyzer? Because the syntax analyzer is working is like this. The working style of syntax analysis is, it takes tokens from lexical analyzer and utilizing context free grammars. All the syntax rules of the program, represented by using context-free grammars. Now what this verifies is what the parser will do. These tokens are members of the grammarship or not. Membership of context-free grammars. Tokens are members. Tokens are generated from context-free grammar or not. This membership is called as parsing. That's why the task done by this syntax analyzer is also called as parsing. That's why this program can be called as parser. That's why there are two names. We can use two names for the parser, can be called as syntax analyzer we can call it as a syntax analyzer or we can call it as a parser. Like this, we have two names for this. Why parser? Because parsing is going on. What is parsing? One string is member of one grammar or not. So a string is member of the grammar or not, known as parsing. Here the task done by the syntax analyzer is tokens are members of context-free grammars or not. Right. That's why to design this parser, we want two things. One is meaning of grammars, designing of grammars, especially context-free grammars. Next one, to design this parser, parsing algorithms. So for the design of parsers, we want to learn these two concepts. One is grammars. How to design a grammar for the given programming syntax, because here nothing is known to the compiler. Whatever we are as a compiler designer, whatever the rules we are providing, based on that rule it is verifying in the program whether the program is there as per the rules or not. How will tell the rules to the compiler? Based on grammars. So here the syntax rules of program will be represented by using grammars. So first, to design a compiler or to design a parser, we should know how to develop grammars for the corresponding programming syntax. So in today's class, we are focusing mainly on designing of grammars, what exactly grammar is. So our discussion will be completely on grammars. So once grammars are over, then to design this parser, we have parsing algorithms. So by using parsing algorithm, how to develop a parser. So let us go and focus on grammars in today's class. So grammar is one of the very important concept. Grammar is a common concept, mainly used in compilers. So most of the phases of the compiler, syntax analysis, semantic analysis, intermediate code generation, these three phases are developed based on grammar's concept. And not only here, in theory of computation subject also, lot of weightage is there for grammar. So from these two subjects together, the grammar topic from this 2 to 3 marks or 2 to 4 marks we can get in the gate paper. That's why usually I say there is no gate papers in computer science without grammar concept, because grammar is a common concept from two subjects. So theory of computation and compiler design. Sometimes grammar's notations will be used even in programming language as well. Okay, right. So this is a advantage of grammar. So let us go and see the concepts of grammar. What are the different concepts available in grammar? See, this terminology grammar, it is not a new one for us. We are not learning this concept today itself. From your childhood onwards, we are learning about grammar. From the childhood onwards, we are learning about this. You might have listened this topic, grammar. English, grammar. Hindi, grammar. Some language, it's grammar. So grammar is some of the common concept whenever we use the term language. So whenever you say there is a language, grammar will be followed by that term language. So what is this grammar? Grammar is nothing but simply rule of the language. See here, set of rules. Whenever we say grammar, grammar is simply nothing but set of rules. Set of rules used to describe strings of a language. Set of rules used to describe strings of a language known as grammar. So here we have set of rules to describe strings of a language known as grammar. So every language having particular rules, that rules representation is grammar. That's why English language, whenever we say English language having particular rules, every sentence should be of this format: subject, verb, object. Like this particular order will be there. Those rules are called as grammars. Like this here in computer science, what is the use of this grammar in computer science? In computer science, we are dealing with so many languages. C language, from the moment you join computer science, C language, C++, Java, Python, this language, so many languages. If you have these many languages, definitely for every language grammar should be there. Here also we have some grammars. Okay. So what are the grammars here? Is it very difficult here? Like in English language, grammars we have subject, verb, object, nouns, pronouns, adjectives, different things. These many things are there in here? No, the grammars of computer science are very easy one. The grammar of computer science defined with just 4 things. Here also we have grammars. C language grammar. See, take the any standard book of C language. We can observe the grammar of that language. Java language, its grammar also. Grammars are there for every language. How these grammars will be represented? How the grammars are represented in computer science languages? Grammars are represented here by using 4 tuple, 4 things. N, T, P, S. This is some people will call it as VTPS also, because N is nothing but non-terminals or variables. What are there? So what things are there in our grammars of computer science? There are 4 things: non-terminals or variables, terminals, number of productions, starting symbol. One starting symbol will be there, non-terminals are there, terminals are there, productions are there. These are the order, can be anything, not an issue. So these 4 things are there in every computer science grammar. Let me write some example grammar, how the grammars looks like. The standard structure of the grammar is like this. Alpha gives beta format. We have an arrow, left side alpha, right side beta. So exact meaning is we can write alpha equal to beta also. Both are same. Alpha and beta are same. So alpha can be replaced by beta, beta can be replaced by alpha. There is one arrow. Here there is one arrow. Left hand side something will be there, right hand side something will be there. Okay. Right. Set of rules used to describe strings of a language known as grammar. So the grammar structure for some example input is, assume we have this one. This is one of the grammar. Sure. In today's class, we are discussing about grammar only, grammar topic. Our topic is going on completely based on grammar. Okay. So the grammars of computer science looks like this. Here there are some arrows. There are some arrows. Left hand side something will be there. Right hand side something will be there. This is the normal structure of the grammar. In every grammar we have 4 things. 4 things. Non-terminals or variables. So in any grammar, what are the non-terminals? We have an example here. In this example, can you identify what are the non-terminals of this grammar, or what are the variables of this grammar? If the grammar looks like this, what are the variables or what are the non-terminals of this grammar? In general, capital letters. You see, grammar will be generally combination of capital letters and small letters. Alphabets of capitals and small. So in general, all the capital letters are called as non-terminals. So if you want to identify non-terminals for this grammar, example grammar, can you identify what will be the non-terminals of this grammar? All the capital letters. So S, A, B, C. These are the non-terminals or variables of this grammar. Okay. In general, small letters are called as terminals. So how many terminals present in this grammar? Like this, whenever a grammar is given, we should be in a position to identify the rules. Whenever we are designing any compiler, rules are like this. So we should be in a position to analyze different information from the grammar. How many terminals? Small letters. How many small letters are there here? The number of small letters will be A, B, D. So total number of terminals of the given grammar is A, B, D. 3 terminals are there. What is the starting symbol? Whatever is the first symbol, is there, that is called as starting symbol. So the starting symbol of the grammar is nothing but S. The starting symbol. Whatever is there in the first position, that is starting symbol. Next one, number of productions. Productions are nothing but these arrows. How many arrows are there? These are called as productions. So can you tell me how many productions present in this given grammar? How many productions present in this given grammar? Arrows are productions. So this structure is called as a production. So there are how many total productions? Thank you, Nishu Kumar. How are you? After a long time. Anyhow, okay. From morning onwards, we are celebrating Teachers' Day today. I wish you happy Teachers' Day for you people as well. If any of you are working as lecturers, faculty somewhere, wish you happy Teachers' Day to you all. Right. Okay, there are number of productions are nothing but 4 productions here. So 4 arrows are there. Total 4 productions. This is the NTPS information. Thank you. Right. Okay. I'm just modifying the grammar. Sometimes grammars will be like this as well. If the grammar is like this, now how many productions present in the grammar? The grammars can be written this way also. Now how many productions present in the given grammar? So whenever the grammar is like this, see the number of productions, whenever we give this, the meaning of this is, instead of writing this is nothing but or, it is a or meaning. So A gives A gives B. This is one production, this is other production. Here there are 2 productions here. So if you want to count total number of productions, 1 production, 2nd production, 3rd production, 4th production, here 5th production, 6th production. Total 6 productions are there in the given grammar, like this. So number of productions, whenever we can use this way also, this gives the 2 productions. If I want to include for the same non-terminal A, if I want to include one more, I can give like this. Instead of this, I can use like this also, or C. A gives or C. So grammar structure will be like this. Now let us see some of the terminologies present in the grammar. So whenever we say grammar, so let us try to analyze some more information from the grammar. I will show you some more grammars. Let us try to identify. This is one more grammar. This is one more grammar. Up to this part. Forget about this handles and all this. This is the grammar. Can you tell me how many non-terminals present in the given grammar? Non-terminals present in the given grammar. How many non-terminals present in the given grammar? So non-terminals are nothing but capital letters. SAB. How many terminals present in the given grammar? Terminals. How many terminals present in the given grammar? Small letters. In general, terminals are nothing but small letters. Small letters, all the small letters present in the given grammar. Identify properly small letters. So, in the given grammar, what are the small letters? A, B, C, D, E. There are 5 things, right? 5 things. Small symbols. A is there, B is there, C is there, D is there, E. Total grammar, in the total grammar, there are 5 terminal symbols. So this I am asking about terminals. Next we will go for productions. How many productions present in the given grammar? How many total productions, arrows? So this is one thing. Here it is 2 and 3 and here it is 4. Total 4 productions. And starting symbol, whatever is there in the first position, that will be normally a starting symbol. Whatever is there in the first position, that is normally starting symbol. So starting symbol of this grammar is nothing but yes. Okay. So like this, initially we have to habituate the grammar productions. Total NTPS information present in the grammar. So this is one of the grammar. Let us try to analyze the information, NTPS information from this grammar as well. So this is the grammar. So this is the capital C, this is the small c. This is small c. This is small c, whereas this is capital C. Okay. Right. How many non-terminals present in this grammar? How many non-terminals present in this grammar? The first symbol will be always starting symbol. What are the non-terminals of this grammar? Capital letters, capital letters. How many capital letters are there here? So S, A, B. Starting symbol also will be included in the starting symbol generally will be included in the non-terminals list. Terminals. How many terminals present in this given grammar? How many terminals present in this given grammar? So terminals of this grammar generally small letters. The small letters present here is A, B, C, D. A, B, C, D. This is a capital C. This is the small c. Both are there here. Now number of productions. How many productions present in this? How many productions present in this grammar? How many productions present in this grammar? In this particular grammar? Number of productions. Number of productions. Productions is the main thing. The number of productions present in this particular is, this is one production, second production, third production, fourth one, fifth one, sixth one. Total there are 6 productions present in the given grammar. 6 productions, and S is the starting symbol. S is the starting symbol. Okay, so this is the total NTPS. Grammars looks in this way, and whenever grammars are there, we have to analyze the information from the grammar as it is. Right. Now we'll go for different terminologies that will be used in grammars. Whenever grammars are there, the first terminology we have to understand from the grammar is derivation. Derivation. Why this derivation is required? Because the grammar, whenever you say grammar, this is the grammar. Grammar will generate some languages, collection of strings. Every grammar will generate collection of strings. Here every symbol comes under one token. So token. So these are called as some of the token sequence. Token sequence. So on what token sequence? Token sequence are called strings. What type of strings these grammars will generate? If you want to know that, for that we have to perform concept called as derivation. Derivation. So derivation is nothing but the process of deriving strings from the given grammar, known as derivation. So whenever grammars are there, from the grammars represents rules of the strings, how the strings will be generated. So that strings generation process is called as derivation. So the process of deriving strings called as derivation. The derivation is of two types: leftmost derivation, rightmost derivation. Leftmost derivation, rightmost derivation. Let us see the derivation example from this. This is one of the grammar example here. So what is the leftmost derivation here? Derivation will always start from the starting symbol. Then this is the meaning of equal. So S will be replaced by its right side, ABC. ABC. So A is replaced by A, B is replaced by B, C is replaced by D. Finally, this is the last step. Here we are getting the string. So generation of the strings from the given grammar, this total process is called as derivation. This is called as derivation. So in this derivation, we'll use two type of derivations: leftmost derivation, rightmost derivation. Observe here, ABD string can be generated this way also. There is a difference. Here, first C will be, look at this. Here first left hand side A will be replaced, but in this C is replaced, then B is replaced, then A is replaced. So derivation, whenever we are using, left to right also we can perform derivation, right to left also we can perform. If we are replacing from left side onwards, one by one, every time leftmost non-terminal replaced, leftmost non-terminal replaced, leftmost non-terminal replaced. If we are doing like this, this is called as leftmost derivation. Sometimes we'll go from right side. Rightmost non-terminal will be replaced first. Rightmost one replaced. In this step, rightmost one is replaced. In this step, rightmost one is replaced. If we are giving priority for rightmost non-terminal for the replacement, that is called as rightmost derivation. Now you tell me, in order to generate strings, you just tell me, in order to generate string, which is the preferable derivation, leftmost or rightmost? If I want to generate strings, which is the preferable one, leftmost or rightmost? Leftmost derivation or rightmost derivation, which is the best one? Which is the best one here? Okay, some people are saying leftmost, some people are saying rightmost. There is nothing like that. This should be best. That is depends on our requirement. Sometimes we'll use leftmost derivation, sometimes we'll use rightmost derivation. There is no one which is best here. So based on requirement, if we go for parsing algorithms, we have two type of parsing algorithms: top down parsing, bottom up parsing. Generally, top down parsing uses leftmost derivation. Whenever you say top down parsers uses leftmost derivation. Bottom up parsers uses rightmost derivations. So top down parsers, in the parsing time also these two will be used, not any particular. Sometimes we use this, sometimes, like if it is a bottom up parsers uses rightmost derivation like this. So both are good. There is nothing that this is only best, this is only best. So based on the requirement, sometimes we use leftmost derivation, sometimes we use rightmost derivation. There is one more terminology called as parse tree or derivation tree. Parse tree or derivation tree. Generally, what could be the derivation tree? Just read it once. Derivation tree or parse tree. Derivation only. Derivation. Tree representation of derivation, known as derivation tree. Tree representation of the derivation, known as derivation tree or parse tree. So tree representation of the derivation, known as derivation tree or parse tree. So derivation, leftmost derivation way we can show, rightmost derivation we can show. Sometimes like this in the tree structure. So S is replaced by ABC, A will be replaced, B will be replaced, C will be replaced. This is called as the parse tree. This structure is called as parse tree or derivation tree. So derivation tree is nothing but derivation which is there in the tree structure. Here the output of the syntax analyzer or parser is nothing but parse tree. Parse tree is nothing but simply from the grammar how the strings are generated. Okay. Is it clear? Parse tree meaning, parse tree can be also called as derivation tree. So most of the times, right, we'll use derivation tree. Derivation tree is a readable format. So we generally use majority of the concepts as in the form of derivation trees. Okay. Okay. So if they based on this derivation trees, we have a concept here from grammars which is called as ambiguous grammars. The grammars, whatever we are observing here, grammars are two types. Grammars generally comes under two types here. Grammars, basically two categories of grammars are there. Some grammars are called as ambiguous grammars. Some grammars are unambiguous grammars. Why we are using these grammars concepts here? To design, we have to design syntax analyzers. But whenever we are designing syntax analyzer, so for designing of syntax analyzer or parser, unambiguous grammars are good. Parsers are difficult to design if the grammars are ambiguous. That's why our concept of designing parser or designing syntax analyzer will work only if your grammar is unambiguous grammar. If the grammar is ambiguous, it is difficult for us to design a parser or syntax analyzer. That's why while developing the grammar, we'll design grammars. While designing grammars, we'll verify whether our grammar is ambiguous or unambiguous. If the grammar is ambiguous, it creates a lot of problems. That's why generally we don't design parsers for ambiguous grammars. If your grammar is unambiguous, then it will best suitable to design our parsers. So We need to verify which grammar is ambiguous, which grammar is unambiguous before development of the parser. Okay. So let us go and see what type of grammars comes under ambiguous, what type of grammars comes under unambiguous. So we have a definition here, ambiguous grammars. Just read it once. Read this definition once. A grammar is ambiguous. A grammar is ambiguous for at least one string, for at least one string, minimum one string, at least one string, if more than one parse tree exists, more than one parse tree exists, or more than one leftmost derivation exists, or more than one rightmost derivation exists. See, if more than one derivation exists, what is the problem? More than one LMD or more than one RMD or more than one parse tree. If any of this presents, the grammar comes under ambiguous. More than one leftmost derivation, ambiguous. More than one rightmost derivation, ambiguous. More than one parse tree, also ambiguous. More than one derivation, ambiguous. See, derivation always gives the particular meaning. That's why different meanings, that will be confusion, that confusion called as ambiguity. Let me explain this clearly. So mainly our more important thing out of all this thing is more than one parse tree. Whenever we generally prove by using more than one parse trees. For one string, different parse trees exist. That is generally considered as ambiguous. Let us see what will be the general problem if a grammar is ambiguous. We have a grammar like this. There is some grammar. For this grammar, for the input n plus n star n, this input also belongs to this grammar. We have different tree structures. For this input, more than one derivation tree exists. See, one derivation tree is like this, one derivation tree or parse tree. This is one tree structure, and we have, so for the same input, we have one more. See here, input is same. Sometimes we are getting this tree structure, sometimes we are getting this tree structure. What is the problem? We have different tree structures. If there are two different tree structures, what will be the problem? These two tree structures are for the same input. We have multiple tree structures here. We have multiple tree structures, but input is same. For the same input, n plus n star n, multiple tree structures are there. Whenever you say any parse tree, whenever you say parse trees, for the parse trees, generally whenever operators are there in the tree, the meaning is bottom level operators having higher levels than top level operators. So whenever we have any tree structure in a parse trees, the bottom level operators are higher precedence than top level operators. Based on this, if you observe, here in this tree structure, we have a plus here, we have a star here. So which will be the higher precedence, tell me? Based on here, we have two tree structures. This is one tree structure, this is one tree structure. Based on this structure, which is higher precedence? Which tree structure is having higher precedence? Based on your knowledge. The lower levels always having higher precedence, no? So which tree structure is having, which operator out of these two, out of plus and star, which operator is having higher precedence? Generally, no. See, from this tree structure, observe only this tree structure, observe only this. Bottom levels are higher precedence than top levels. So we have plus operator, we have star operator. which operator is the higher precedence from this tree structure? Plus, because plus is there in the bottom level, so plus is higher than star. Plus is higher precedence than star. Observe this tree structure. In this we have star here, we have plus here. Out of plus and star, which is higher precedence? Which operator is having higher precedence? In this tree structure, star is there in the bottom levels, plus is there in the top levels. So star is higher precedence than plus. Star is higher than plus. Okay. Sometimes, so here different meanings we are getting. There are just two operators, plus and star. Sometime some tree structure is saying plus is higher precedence. Some tree structure is saying star is higher precedence. That means it is giving two different meanings. Okay. Assume I am using compiler is producing this tree structure. See, whenever operator precedences are there, whenever you want to evaluate any expression, which operator is higher precedence, which is lower precedence, that information should be provided by compiler to the processor. So this operation should be executed first. Star multiplication should be, then plus. That information will be given by compilers to the processors. So if compiler should have a clarity first, if it is giving, if it is telling to the processor, it should have the clarity first. Compilers generally maintain these precedences based by using tree structures. So assume this tree structure is designed by compiler, produced by compiler. Then the compiler is saying that plus is higher precedence than star. Assume we have an expression 2 star 3 plus 4. 2 star 3 plus 4. Assume we are having this one 2 star 3 plus 4. So if we want to, if compiler is saying that plus is higher precedence than star, plus is higher precedence, what output will be produced for this, say, this expression? Plus is higher, no? First this is executed. This is executed. 5. So 2 star, 2. This is plus 7. Plus is executed first. So this is 2 plus 2 star 3 plus 4. So this value of the expression, this is 7 multiplied with 2. The 14 answer will be produced. Okay. Assume compiler is producing this tree structure. For the same expression, 2 star 3 plus 4. If whenever this tree structure is produced by compiler, it is the meaning of star is higher precedence. Star is higher precedence. So whenever a star is higher precedence, then how this value will be evaluated? This is executed first. 6. Then plus 4. 10. See, value is same, right? What expression is same. 2 plus 3 star 4. If compiler is producing this tree structure, we are getting answer as 14. Compiler is producing this tree structure, we are getting answer as 10 here. 10. Like this, for the same expression, different answers. Dilemma, confusion. Now, this is correct or this is correct. Like this, we have multiple tree structures. Which tree structure to be produced? This dilemma comes to the compiler. This dilemma is because of this type of grammars. This type of grammars are called as ambiguous grammars. That's why if a grammar is ambiguous, that is a lot of confusion to the compiler. Ambiguous grammar. Whenever a grammar is ambiguous, the parser of compiler or compiler will fall into dilemma, will fall into confusion. That's why generally what we will do while designing compilers, if we have any ambiguous grammars, we'll just keep aside those. We'll not give preference to design parsers, syntax analyzers by using ambiguous grammars. That's why first whenever grammars are designing, first we'll detect whether the grammar is ambiguous or not. If the grammar is ambiguous, we'll keep that grammar aside. Then we will design parsers. We'll use unambiguous grammars generally to design syntax analyzers or parsers, because like this. Now you got the meaning of ambiguity. So what type of more than one parse trees exist? Ambiguous. So more than one, that also meaning though, that also gives the meaning of more than one leftmost derivation, which also gives the meaning of more than one rightmost derivation. Anyhow, more than one derivation, that can be in tree structure or in leftmost derivation or rightmost derivation, any one way is there. More than one gives more than one meaning. If multiple meanings are there, confusion to the parser. That's why that more than one meaning things, meaning grammars, generally we'll remove to design parsers. We'll avoid to design parsers. Is it clear? So now we'll see few examples. What type of grammars generally comes under ambiguous grammars. We'll take few examples of how we'll identify which type of grammars comes under ambiguous grammars. So this is one of the example. Very simple like this. We have to identify any one single string. Here these are different. Its left child is growing, right child is growing. Here plus is there in bottom levels, here star is there in bottom levels. Both are different trees for the same input. This type of grammars generally comes under ambiguous grammars. Right. So I am taking one example here. Is this grammar comes under ambiguous grammar? Is this an ambiguous grammar or unambiguous grammar? The question is, the grammar is ambiguous or not? The grammar is ambiguous grammar or not? We need to find. How? You need to identify any string, identify any particular string for which more than one tree structure is there or not there. For at least one string, more than one parse tree is there. That comes under generally ambiguous. So we need to find such type of string. So generally, let us take a string called as AAA from this. How to identify directly? It is difficult. We have to go one by one. Take one length, two length, three length like this. Ambiguous. Whenever ambiguous, that for which input it is showing ambiguous. So for AAA, we have different possibilities. This is one tree structure possible for AAA. Whenever three A's are there, first S gives AE, this one replaced by this one replaced by this, here by this. 3A's will be generated. This is a one way we can generate 3A's. We have one more way here. From the left child, I will take. This is one more way. See here, in this tree structure, we have for the same input. For the same input. We have different tree structures. This is one tree structure. Right child is growing. We can say we are using rightmost derivation here. For the same thing, left child is growing. We are using leftmost derivations here. Like this, different derivations can be or different tree structures can be. So different tree structure is there. Right child is growing. Here, left child is growing. For the same input. Every tree will give different meaning. That's why different tree structures are there. dilemma, confusions. It creates these type of grammars, creates confusions to our parsers. That's why these type of grammars are called as ambiguous grammars. Hence, ambiguous grammars will not be giving preference. We don't give preference for ambiguous grammars to design parsers. Okay, like this. So this is one of the fundamental thing. We have to design grammars. We have to design grammars to represent syntax of statements. But to design parsers or syntax analyzers, ambiguous grammars are not at all good. It will provide unnecessarily confusions. So unnecessary confusions it will produce. That's why we'll detect ambiguous grammars, we'll remove them, ambiguous grammars, to design parsers. Okay. So this is the basic information related to ambiguous grammars. So I can give you one question. You can practice this question. Find this grammar is ambiguous grammar or not. Find this grammar is ambiguous or not. Ambiguous finding is one of the very common questions that we can observe in gate papers. There are so many questions from given grammar is ambiguous or not, or ambiguous is one of the fundamental property to design parsers. That's why, so this is one normal question. You can you can practice, you can take it as a homework and find out whether it is ambiguous or not. Okay, so in today's class what we have discussed is, so what exactly grammar? So grammars are generally used to represent syntax. Grammars are used for syntax. Then every grammar is not good. We have derivations. So ambiguous grammars, multiple derivation things. Ambiguous grammars are not good to design parsers. These are not good for parsers. Okay, so this is about today's discussion. So with this, today's class we can stop here, and tomorrow onwards, and different concepts on grammars, and with using those grammars, how to design parsers by using parsing algorithms. So those things we are discussing in from tomorrow onwards. Okay, any doubts in today's session? Now you can ask your doubts if you have any doubts from your side. So what I am saying here is, to design parsers, first we are getting some fundamental information from grammars, because total parsing, semantic analysis, intermediate code generation, all about grammars only. That's why we should have a basic information about the grammars. So what type of things comes under ambiguous grammars? What are unambiguous grammars? So leftmost derivations, rightmost derivations, first calculations, follow calculation. So many things are there from grammars. So in today's class, I have given just an introduction for grammars. Okay. Okay, guys, that's all about today's session. Thank you all. Once again, wish you happy Teachers' Day. If any of you are already in the teaching profession. Okay. Thank you. We'll see in the next class with some other new concepts. When you counted terminal, how we counted 6 instead of 5 in previous slide. See, terminals are nothing but small letters. Small letters. How many small letters are there? Those many terminals generally will count. Okay. Generally, small letters are comes under grammar terminal symbols. So if it is in a grammar, how many small symbols are there? Those are terminals. Okay. Okay, guys. Thank you all. Bye bye. See you in the next class.